Welcome, Calc students, to our video notes section on 3.1, which is our first section in our new chapter 3, which is all focused on applications of derivatives. So one main application of derivatives, as you'll see, are locating extrema on an interval. So what is extrema? It's basically just the plural for extreme values. So what are extreme values? They are maximum and minimum values of f. And when I say maximum and minimum values of f, I'm referring specifically to the y values or the outputs of a function. So we're talking high points and low points on a graph. So we've got four different kinds. We've got absolute min and absolute max, and then we have relative min and relative max. So the main difference between absolute and relative is absolute is the lowest. When I'm talking about a minimum, it's no y value gets lower than the absolute minimum. And the absolute maximum is the highest. No y value gets higher than the absolute maximum of a function on an interval. What's a relative minimum? A relative minimum is when you're you're in a particular portion of the interval. So it's like a neighborhood, a real localized place on the graph. And at that point, the functions hit like a valley, a low point on the graph. That's considered a local minimum. So it's not necessarily the lowest y value, but it is a low point on the graph relative to the other nearby points around it. And a relative max is like a peak, right? A high point on the graph relative to the points around it. So these are also called local maximums because if you localize them to one particular area on the graph, they stand out as a high point, but they're not necessarily the highest point like an absolute max would be. So if you look at this picture right here, we've got this function that kind of oscillates, and it's between these endpoints here of a to b. And you can see, okay, the absolute max is the highest y value that the function reaches, okay? The absolute min is the lowest low, the lowest y value that the function reaches. But along the way, it hit other high points and it hit other low points, or maybe started at a low point. So endpoints can also create relative high and lows. So these are all considered relative maxes and mins. So this high point right here, right at the peak before the function turned around, and then again it went up here and turned around. Those peaks that it hits are considered relative max, even if they're not the highest max. And then this starting point and this sharp turn right here were places either where the function began or where it turned around that were low points relative to the other nearby points around it. Even though they weren't the lowest, they're still considered relative mins because they're low points on the graph relative to other points around it. So these are all referred to as extrema, and we can use the derivative to help us locate where those are. But before I show you how to do that, I want to point out a couple other theorems and phrases for you to understand. The next thing I want to talk about in this video is another important theorem to add to our list of important theorems, and that is the extreme value theorem. So this question is very important, and there will definitely be questions on the AP test that require you to know this to be able to get it right. And as with all theorems, it starts with the conditions. So there's two of them. The first one is f has to be continuous. And the second one is it has to be on a closed interval. And if those conditions are met, then the result is that f is guaranteed to have both an absolute minimum and an absolute maximum on the interval. So let me just kind of go through these three pictures. These are like three scenarios, same function, by the way, in every scenario. Except in scenario 1, we can see that f is continuous and on a closed interval. So we can see both of the conditions of this theorem are met. Both conditions met. So what's guaranteed? We have an absolute maximum of 5 and an absolute minimum of 1. Guaranteed, a highest and a lowest on the interval. Okay, in the second scenario, we can see f is continuous. So first condition's met, but the interval is open. So only one condition is met in this second scenario. So notice that if you don't include the endpoints, that means they're open circles, right? They're not included. Well, if one of those was providing your max or min, I can no longer use it anymore. So in this example, I no longer have a highest y value. I still have my absolute min, right? So this theorem doesn't say that you won't have a min or max if these conditions aren't met. It's just they're not guaranteed. Having both conditions met guarantees an existence of a highest and a lowest. Only having one condition met or no conditions met means you might have an absolute max or min, but it's not guaranteed. So this one did have an absolute min, but not an absolute max. Because even if I chose like 4.9, for example, well, then you could say, well, what about 4.99? Right? That's higher than 4.9, but not quite 5. Okay, what if I chose 4.999 or 4.99999? There's like infinite amount of numbers between 4 and 5. So if I can't actually let it hit 5, then I don't actually have a highest. Okay, and then over here in the last one, again, I have G is not continuous, so it's not meeting the first condition, but the interval is closed. So G is not continuous because right here there's a hole and the function has a different y value than the limit, right? The limit at 0 is not equal to G of 0. You can see that kind of right here. They changed the value there. So then what used to be my absolute minimum is no longer a minimum because they changed it to 2, which is not the lowest, right? There are y values on this that are lower than 2. I still have my maximum at my endpoint, right? My interval was closed, so I still had that maximum, but I was not guaranteed both because only one condition was being met. So this is kind of showing you 3 scenarios that were either meeting both conditions or only one. Now I want to show you scenarios where you're not given an interval at all. So let's look at this one here. It's basically a linear function. So if you close off the interval and you define it on the interval from A to B, then all of a sudden you've got definitely an absolute minimum here and an absolute max there. Let's take that same graph, but without the interval. So no interval at all, just this linear function. Well, all of a sudden it doesn't have a max or a min because the function extends forever in both directions and there's no highest or lowest point at all because I didn't close it off anywhere. I didn't choose an interval. So just the very act of giving a function endpoints creates max and min values. And this function here, suppose again, I didn't cut it off and I just let the function continue. And so maybe it was something like that. I still have relative mins and maxes, but actually I still have my absolute min. Look at that. I still have my absolute min. So the function or the theorem doesn't say you won't have an absolute max or min if the conditions aren't met. It just says that you're not guaranteed. So in this one, I still have my absolute min, but this is no longer an absolute max anymore because if I don't have an interval, if I don't have endpoints, and I just let the function extend forever, both of these arrows are going up, meaning these y values will eventually overpass this one. And it's no longer the highest y value anymore. And there is no highest y value because these will continue extending up. And there will not be a highest y value. So it only had the min because there was no interval. And then a similar thing here. So if I didn't close it off, you know, who knows what the rest of the function does. I may still have, let's say I may still have my absolute max without the interval, but without these endpoints, and the function's allowed to keep going down, let's say both ends are going down, there's no absolute min because these arrows are going to go beyond what would have been my lowest y value, and because they continue to extend, there won't be a lowest y value, just relative mins, but not absolute min. So in the extreme value theorem, it's all about having endpoints. The fact that you're stopping the function at an endpoint is what allows there to have a highest and a lowest point on the graph. So that's why those 2 conditions are really crucial in the extreme value theorem. The function definitely has to be continuous because every point has to connect, right? You don't want to have any holes or anything. But it's got to be on a closed interval. That action of closing off the interval, right here, we had endpoints here and here. is what guarantees both the absolute min and the absolute max. Now, another thing I wanted to talk about is this thing called a critical point. This is what we call a value of x that makes the derivative either equal 0 or makes the derivative undefined, not exist. The extreme values are basically where the function f has a turning point, right? Where your function is turning around, you will find that that creates a max or a min if it was going like this. If it had been decreasing and turned around or going something like that, it's at these turning points where the function changes direction. That's where you're going to have a max or a min. Well, if the function is smooth and it changes direction, so like this or like that, then your tangent line will be horizontal, right at a turning point. Your slope of your tangent line will be 0. So that's the situation where f prime of c is 0, would be at a turning point on a function that's nice and smooth. The other option is your function's turning around, but it's like a sharp turn, like a corner or a cusp. So where you have a corner or a cusp, sharp turn, is where your derivative does not exist. So these two things can help us locate where all of the turning points are, where all of your maximum or minimum values are. Either at a horizontal tangent line if the graph is smooth, that's when the derivative is 0, or at a sharp turn, a corner or cusp. So we use this fact to locate all of our relative extreme values, our relative and absolute extreme values. It's going to either happen at those critical numbers where derivative is 0 or undefined, or at endpoints like here and here. So example 1 here is really meant to just sort of drive that point home. So we've got 3 equations here, and we've got their graphs shown for you. And we want to basically find the derivative and evaluate what it would be at this extreme value here to see, is it 0 or is it undefined? So in this first one, I'm going to go ahead and just simplify the function a little bit because I can distribute the 9. I also can rewrite it as 2 separate fractions because they have a common denominator, so that helps me not have to use the quotient rule when I do it that way. I can think of this as 2 separate power rules. I can cancel out those x's, by the way. So I get 9 over x minus 27 over x cubed. So then that can equal 9 times x to the negative 1 power minus 27 times x to the negative 3rd power. So that's my f of x function that I'm going to use here. So when I take the derivative of that, I can just use power rule, 2 power rules. So I get negative 9x to the negative 2 plus 81 times x to the negative 4th, which is equal to negative 9 over x squared plus 81 over x to the 4th. Now in the graph over here, we can see the function was increasing. It hit a high point when x was 3 and then began to decrease after that. So what I'm going to do is evaluate f prime at 3. So I get negative 9 over 3 squared plus 81 over 3 to the 4th, which is negative 9 over 9 plus 81 over 81. So I end up with negative 1 plus 1, which is 0. What is that doing? That's just confirming the fact that when you hit an extreme value, a turning point on the graph, like we have here on this graph at x equals 3, the derivative will in fact equal 0. Why is that here? It's because if I were to draw a line tangent to this curve right at the peak, the tangent line would be horizontal, and the slope of a horizontal line is 0. And the derivative of a function at a point is the slope of the tangent line at that point. So the slope of the tangent line is going to be 0 when you are at a turning point on the graph of f, at a peak, which we are in this case, or a valley, and this is just confirming that. The same is true if you're at a sharp turn, like a corner or a cusp. So here, I'm going to go ahead and just rewrite this function. This is absolute value function, but I can rewrite it as a piecewise. The absolute value of x minus 1 will equal the same thing, x minus 1, if x is greater than or equal to 1, because these values would keep the inside of the absolute value positive, right? I want to find what makes that positive. I can set the inside of the absolute value greater than or equal to 0 and add 1, and I can see, okay, for x's that are greater than or equal to 1, this value will stay positive, which means the absolute value won't change it. But for x's less than 1, like 0, -1, if I plug those in for x, I would have negatives in the absolute value. So the absolute value would then change the sign and make it opposite. So I'd have the opposite of x minus 1. So you can see that too on the graph here. Let me simplify a little bit. So I've got x minus 1 for x greater than or equal to 1. I've got negative x plus 1 for x less than 1. So what does that mean? That means when you come in and find the derivative, it changes abruptly. On the right of 1, the slope is positive 1. That's when x is greater than 1. But on the left of 1, the slope is negative 1. And it just changes very, very abruptly right when x equals 1. It is not a smooth transition between slopes. So basically f prime of 1 does not exist because the left-hand derivative and the right-hand derivative are not equal. So left-hand derivative does not equal right-hand derivative at x equals 1. It was an abrupt change in slope. So that's a corner. But notice that corner is also the minimum value on this graph because the graph was decreasing and then abruptly changed and increased. It was a turning point. So this corner, where the derivative did not exist, located a minimum value on the graph. Why don't you guys do this u-try here? So in taking this derivative here in the u-try, we can use a power rule and a chain rule. So I start by multiplying the power in front, 2/3, and then subtracting 1 from the power to get negative 1/3, and then multiplying by the derivative of what was inside, which was actually just 1 in this case. So then because the exponent is negative, I move it to the denominator. The 3 is in the denominator as well. And you can either leave it like this or rewrite it as a cube root. And then in this case, our minimum value for this graph was at -1. So if I plug -1 into my derivative, it creates a 0 in that cube root, which is now in the denominator, right? Because when I subtracted 1 from this earlier power, it made it negative. So this x plus 1 ended up in the denominator, creating a 0 in my denominator, which, as you know, on the graph of the derivative would make a vertical asymptote, meaning the derivative does not exist there. Random dividing by 0 does not exist. So that's because there was a cusp on the original function. Now what is a cusp? A cusp is a sharp turn. So the function was turning around. So this place where the derivative didn't exist could help us to locate what turned out to be the minimum value on the graph. So the point is this. If your function is going to have a minimum or a maximum, like this one did, it will happen at a turning point, whether the turning point was smooth or sharp. So locating smooth turning points, you locate where the derivative is 0. Locating sharp turns, you locate where the derivative does not exist. And that is how we find extreme values on an open or closed interval. We start by finding the critical points of f. So again, what are critical points of f? Points that make the derivative either 0 or undefined. Does not exist. So we find the derivative and then we determine those values. That helps us locate the critical points. Then we plug these critical points into our function to find the y value, because remember the y value tells you whether, like, what the max or min is, and it will help us also decide whether it's a max or min. We also want to check endpoints though if we're given an interval. Sometimes we're given an interval, and when in that case, the endpoints are guaranteed to either be a min or a max, so we always check those as well. So these are basically the steps we follow to find all of the extreme values on a function, both absolute and relative. Let's try it here with example 2. So in example 2, we're being asked to find the extrema of this function. So this has no interval. So we're looking for the absolute max and mins and relative max and mins over the whole real number line for this function. So I'll start by first finding the derivative. And I just need to use a couple power rules. 4x cubed minus 16x. So that's the derivative, and then I need to figure out when that is equal to 0. So I set it equal to 0, and now I need to solve for x. So since it's a polynomial, I'm going to solve by factoring. I'm going to pull out a 4 and an x, and then I'll be left with x squared minus 4, right? All of this is equal to 0. And so I will go ahead and factor this further. It's a difference of squares, so I can break it down into x plus 2, x minus 2. And then I can go ahead and set each of these factors equal to 0 to solve by factoring. So I notice when I do that I end up with 3 critical points. 1 when x is 0, 1 when x is negative 2, and then the last one when x is positive 2. So 3 places where this function will have a maximum or a minimum. So now what we do once I get my critical points, I'll go ahead and put them in order, is I plug these numbers into the original equation because I'm trying to figure out where that function hits high points and low points. So I'm going to plug it into the x to the 4th minus 8x squared equation. So when I plug in negative 2 into that equation, I end up with, this becomes positive 16 minus 8 times positive 4. So 16 minus 32, I get a negative 16. When I plug in 0, I just get 0. And when I plug in 2, I get the same thing I got when I plugged in negative 2, 16 minus 32. So I can see from my table that I've got minimum values of negative 16 and negative 16, and then what looks like maybe a maximum of 0. So it also helps, by the way, to confirm with your graphing calculator or graph it on a graphing calculator, because we have the analytical process which will locate the lows and highs, but to know whether it's absolute or local or max or min, it helps to kind of match it to the graph. So these points at negative 2, negative 16, and 216 are these ones right here. So I can see that those are absolute minimums. Whereas with 0, it's right here, 0, 0. I can see that it definitely is a high point over this neighborhood, right? There's all these negative y values, and then all of a sudden it gets up to a high of 0 in this little local area. But since the function is going to continue increasing on the right and left, it doesn't have a highest. We can see that we don't have an absolute maximum, just a local maximum on that neighborhood there. So this is our local maximum. So we can say that f of x has an absolute minimum of negative 16. So remember, the minimum or maximum value is the y-coordinate, and then the x-coordinate locates it. So we would say it has an absolute minimum of negative 16 at the x values of positive and negative 2, and it has a local maximum, local or relative, whichever one you want to say, of 0 at x equals 0. And that would be our extrema for part A of example 2. Now, in part B of example 2, you can see no interval was given. However, you can also see that this function contains a square root, and that's going to limit our domain, which is going to basically give us an interval, which will have endpoints. So whenever you're working with square root functions, you have to remember that the part that's inside, the 4 minus x squared in this case, has to stay greater than or equal to 0, or else it's not in the domain of the function, in which case it would create endpoints. It would not continue to the left and right on the x-axis forever. So 4 minus x squared is going to be greater than or equal to 0 when 4 is greater than or equal to x squared. Or let me write it this way, when x squared is less than or equal to 4. So for this part, we have to just kind of think about what those numbers are to keep in order for me to square them, and they stayed less than or equal to 4. So we've got the one obvious part, which is that x would have to be less than or equal to 2, right? I wouldn't want it to be like 3 or 4, because if I square any of those numbers, that'll be bigger than 4. But the less obvious part, which is also important, is that x has to stay greater than or equal to -2. Because if x were to be, say, -3 or -4, right, something less than -2, and I squared it, those squares would become positive, and then I'd be doing 4 minus a value greater than 4, which would no longer be positive. So this is the domain for the function here in part B. And since the domain is restricted, that basically gives us an interval, right? I can include the endpoints because this function is defined when I plug in -2. I would just have a 0 under the square root, which is okay. So I can include the endpoints, but I cannot go outside of this interval. So that means that I'm going to have a max or a min at these endpoints. Now over here I have the graph for this equation. So this is basically a half circle with a radius of 2. So it's going up to the y-axis at 2, and then to the left and right on the x-axis at 2 and -2. And you can see it does not go beyond that. So just looking at the graph, you can see that both of those endpoints are going to create absolute minimum values. But I'm going to show you how to find that analytically as well. Just like with any other function, I'm going to have to find the derivative, and then I need to figure out what makes the derivative 0, but also in this case, what would make the derivative undefined. So it might help actually if I first remember that this function is a power function. It's 4 minus x squared to the power of 1/2. We have to kind of keep that in mind. That'll help me when I do the derivative because I can use a power rule. So I bring the 1/2 in front, and then I subtract 1 from 1/2, giving me a -1/2 power. But then I also need to use the chain rule because the thing inside of the square root was more than just x, and it has its own derivative. So I need to multiply by its derivative, which is -2x. So I'll do some simplifying here, right? The 2 and the 1/2 can cancel. I do still have a negative, and the x would be in the numerator. So this would be -x in the numerator, but it would be over 4 minus x squared to the power of 1/2 in the denominator. And maybe I'll put that back into radical notation. So it's -x in the numerator divided by the square root of 4 minus x squared. So remember, I wanted to find what value of x would make this derivative equal to 0. Whenever you have a fraction like this for your derivative, the value that would make it 0 comes from the numerator. So when a numerator of a fraction is 0, the whole fraction is 0. So I really only have to focus in on the -x part and just set that equal to 0, which would be basically when x is 0. So this is one of my critical points because it makes the whole fraction 0. But the other thing we have to pay attention to when we have a derivative that's a fraction is when the denominator is 0. Because if the denominator is equal to 0, then that makes the derivative undefined, which is also a critical point. So I'm also going to need to set the square root of 4 minus x squared equal to 0 to find when the derivative does not exist. So I could start by squaring both sides, which would still give me a 0 on the right side, subtracting 4 from both sides, dividing both sides by -1, and then square rooting. And when I square root, I get positive and -2 for x. But you may recall those were also my endpoints over here, positive and -2. So they're endpoints and they're critical points. So it's like a double whammy. They're definitely going to be a max or a min. So then I take my critical points and I evaluate my function at them. And remember, when I do that, I plug them into the original equation because I'm trying to find the max and minimum values of f of x. So I plug them into f of x. So I have -2, 0, and 2 again, just kind of like the last one. So when I plug -2 in here, I get the square root of 4 minus -2 squared, which is the square root of 0, which is 0. When I plug in 0, I get the square root of 4 minus 0 squared, which is the square root of 4, which is 2. And then when I plug in 2, I get 4 minus 4 again inside the square root. So square root of 0 is 0. Of course, you can see that on the graph here as well. I can see that the zeros are my absolute minimums. There is no value lower than 0 on this graph. And 2 is my absolute max. There is no y value that goes higher than 2 on this graph. So notice this function is continuous, right? And it is on a closed interval, so it met both of the conditions for the extreme value theorem. So it was guaranteed to have both an absolute min and an absolute max, and it has both. So maybe I'll put the final answer down here. We'll say it has an absolute minimum of 0, right? That's the lowest the y value goes, and that was at the x values of positive and negative 2. And then it also has an absolute max, and the absolute max is equal to 2 when x was 0. So this function basically has a very limited range and a very limited domain. And so that's our answer for example 2b. Now in example 3a, you may notice that we're being asked to find the extrema like we were in the last example, but this time we're given an interval. So that means we're given endpoints. And so after we find our critical points and we're checking them, we need to also check these endpoints, because when you have a closed interval, you're guaranteed that the endpoints are going to give you either a max or a min. So I'm going to start by finding the critical points, right? So step 1, we're going to go ahead and find the critical points, which is basically, so we have to find f prime of x. We have to set it equal to 0, and we need to solve for x. That's basically how we find critical points. So for the derivative, I would get 12x to the third minus 12x squared, because I'm just taking the power rules of both of those. So that's my derivative, and I need to find when that is 0. So I'm going to solve this by factoring again, like we did in example 2a. I'll take out a 12x squared, and I'm left with x minus 1. And then I'll set my two factors equal to 0 to solve. So here I could divide by 12 and then square root both sides, and I just get 0 for x. Here I can add 1 to both sides and I get 1. So I have two critical points. That's what these are called. These are called critical points because these are values of x that if I plug them into the derivative, if I plug them in here, will give me a 0. So I'm going to go ahead and check these values with my original function, and I'm going to also check my endpoints. Okay, so I have got endpoints at -1, critical points of 0 and 1, and another endpoint at 2. And I'm going to plug all of these into my original equation to see which ones are the highs and which ones are the lows. So when I plug in -1, I get positive 3 plus 4, because this -1 cubed would still be negative. I get 7. When I plug in 0, I get 0. When I plug in 1, I get 3 minus 4, which is -1. And then when I plug in 2, I get 3 times 16, which is 48, minus 4 times 8, which is 32. So I get 16. So looking at my values, it looks like I have like maxes at 7 and 16, and then maybe mins at 0 and -1. But this is where it's really important that we check with the graph. So this is the picture that I got off the calculator, but let's go ahead and take a peek right now. And I noticed that it's only between -1 and 2. So maybe I'll change my x window to match that. Maybe I'll have my x scale go by halves. And then I want my y value to at least go up to 16. So maybe I'll have it go a little higher than that, maybe 20. And let's take a look at the graph. So I kind of zoomed in a little bit because I wanted to look at this, but only between -1 and 2. And so I can see that my endpoints are relative maximums, right? This is my endpoint at -1, 7, and then my other one at 2, 16. Those are definitely, this one's the absolute max, obviously it's the highest. This one's a relative max because in this interval it's a high point. And then I do have a minimum here at -1, right? It's my absolute minimum. But what I want you to notice is right here at 0, it's actually neither a min nor a max. Maybe I'll zoom in a little on the y-axis. I had to go high enough to see the maximum, but maybe I can bring the minimum down a little. See if it can kind of show us a little better what's happening there. It's basically not a turning point. So sometimes a function can do that. It can kind of like flatten out without actually changing direction. So this function was decreasing up until 0 where it flattened out, but then after 0 it continued to decrease. Maybe I'll zoom out on my x-axis just really quick so you can kind of see that a little bit better. Maybe this will help, I don't know. But you can see it was decreasing and then continued to decrease. It didn't actually ever like change direction in here. So it was not actually a turning point at 0. And so that happens sometimes where just because a derivative is 0 doesn't guarantee that the point there will be a max or a min. It goes the other way around. If you have a max or a min, that'll definitely happen when the derivative is 0 or undefined. But just because your derivative is 0 doesn't necessarily mean it's a max or a min. So you really have to check the graph to know for sure. Now in future sections we're going to learn another way to tell. It's called the first derivative test. But for now we just sort of look at the graph and go, okay, it didn't actually change direction there. No change in direction, which means no extreme value, no max or min. So what we have is a relative max of 7 at x equals -1, an absolute max on this interval. So this would be my absolute max, my local max. This is an absolute min, and this is an absolute min even if there was no interval, but it's definitely the absolute min on the interval. And then this is neither a max nor a min, neither a max nor a min. It was not a high or a low point. It was just a place where the function sort of flattened out before it continued to decrease. So we'll say that this function has an absolute max of 16 at x equals 2. It has a relative max of 7 at x equals -1, and a absolute min of -1 at x equals 1. And this is on the interval, right? Because this is if you cut off the graph, on the interval from -1 to 2. So in our example 3b, again, we're given an interval, but notice it's open. So if it's open, then that means you don't have to check endpoints. We're only going to check critical points, but we will check our critical points within the values of 0 to 2 pi, and we won't worry about extending beyond that. So here's my equation here. I need to find my critical points, which are where the derivative is equal to 0 or is undefined. So I'm going to go ahead and find my derivative. So the derivative of secant is secant tangent, and there's a constant of 2, but the constant multiple rule just says bring the 2 down and multiply it to the derivative. So 2 times secant theta times tan theta plus the derivative of tan theta, which is secant squared theta. So there's my derivative. I need to find when that is equal to 0. So I'm going to also solve this sort of by factoring. I notice there's a common factor of secant between the two. So I will take that out, and I'm left with 2 tan theta plus secant theta as my other factor, and then that's equal to 0. So I'll set each of these factors equal to 0. So secant theta equals 0, and then 2 tan theta plus secant theta equal to 0. Now, you may or may not recall the graph of secant. It looks kind of like this. It's got the asymptotes at negative pi over 2 and pi over 2 and 3 pi over 2, basically all the odd pi over 2s. And then it has a minimum of 1 and maximum of negative 1, and it kind of makes these parabolas that go up and down. But my point is it never equals 0, right? The value of secant never ever crosses the x-axis, so there is no solution to this part. So that part is not going to make the graph equal to 0. But I will say that it is undefined when theta is pi over 2, because we're also trying to find critical points. But the only thing is, so when theta is pi over 2 actually is not even in the domain of this function. So it's not only the derivative that's undefined there, it's the whole function's undefined. So it's just a point of discontinuity. You can see, right, this graph has asymptotes at the pi over 2 and 3 pi over 2. So I should probably make a note of that earlier. So these are not critical points because they're not even in the domain. So that secant theta was not causing my derivative to be 0. So I'm going to get my solutions from this other factor. And I think I'll change them to be in terms of sine and cosine. So tangent is sine over cosine. And then secant is 1 over cosine. So I notice I have a common denominator between the two. So I'm just going to combine that together and get 2 sine theta plus 1 over cosine theta equals 0. So again, I have a derivative that's a fraction. So when I have a derivative that's a fraction, only the numerator can actually make the fraction equal to 0, right? So I just kind of take a look at the numerator to see when that is 0, because if my numerator is 0, my whole fraction is 0. So I would subtract 1 from both sides and then divide by 2. And so basically I'm trying to figure out when sine of theta is equal to negative 1/2 between 0 and 2 pi. So you think back to your unit circle. So sine is negative when you're in the third and fourth quadrant. So I need to find those two answers. And it's negative 1/2 at the pi over 6's. So it's at 7 pi over 6 and 11 pi over 6. So those are two critical points right there. 7 pi over 6 and 11 pi over 6. Those are my two critical points. But I also have to look for when the denominator is equal to 0. Because if the denominator of a fraction is 0, then the fraction's undefined. And so when my derivative's undefined is another place where there could be critical points. But we kind of already addressed these earlier, because cosine theta is 0 when theta is pi over 2 or 3 pi over 2. But those are already not even in the domain, so they can't be critical points. So these are my two critical points, 7 pi over 6 and 11 pi over 6. So also over here, I want you to know when I was plugging this in my calculator, I made my x-axis go in terms of pi over 6. So that would be here, let's see, 1, 2, 3, 4, 5, 6, 7, right there, 8, 9, 10, 11, right there. So those are my, and you can see those are the highs and the lows, right, where the derivative is 0. So I need to evaluate this function at those values. So when I plug them in to the original equation, so I'm going to plug in 7 pi over 6 and 11 pi over 6. Maybe I'll do a little bit of that work off to the side. So secant of 7 pi over 6, so remember we're in quadrant 3 there when you're at 7 pi over 6. And the coordinates there are negative rad 3 over 2 and negative 1/2. And secant is r over x, r is 1. So it's 1 over negative rad 3 over 2, which is basically negative 2 over rad 3, which is basically negative 2 rad 3 over 3. Except I'm multiplying it by 2, so that'd be negative 4 rad 3 over 3. And then tangent at that angle is y over x. So tangent of 7 pi over 6 is negative 1/2 divided by negative rad 3 over 2, which equals positive 1 over rad 3, which is the same thing as rad 3 over 3. So tan of 7 pi over 6 is positive rad 3 over 3. So then if I combine my like terms, because I have two terms with rad 3, I have negative 4 plus 1. So I get negative 3 rad 3 over 3. The 3's cancel. I get negative rad 3. So that's my value for y when the x is 7 pi over 6, or when the theta is 7 pi over 6. Now at 11 pi over 6, it's the same values, except I'm over here now, so the x is positive. So instead of it being negative rad 3 over 2, negative 1/2, it's positive rad 3 over 2 and negative 1/2. So for secant, actually that means it's positive 2 over rad 3, which is 2 rad 3 over 3, times 2. So I get positive 4 rad 3 over 3. And then tangent becomes negative because now the x value is positive. So now it's negative 1/2 divided by positive rad 3 over 2. So it's negative rad 3 over 3. So now it's 4 minus 1, or positive 3 rad 3 over 3, which equals rad 3. So looking at my graph, see now looking at your table, you might think, oh, this one's the max and that one's the min. But looking at the graph, you can see actually this one right here that was negative rad 3, that was the relative max, because in this interval it was a high point. And the one that was positive rad 3, you can see from the graph, was actually a min, relative min, because it was like a low point in the given interval. So that's why we have to look at the graph, because sometimes the y values can fool us. So it turns out we had a relative max of negative rad 3 at theta equals 7 pi over 6, and a relative min of positive rad 3 when theta is 11 pi over 6. So what I'd like you guys to do is to try this challenge problem. See if you can find the extreme values of this function on the interval. Notice this one's closed, so you'll have to check endpoints as well. And that's right here and right here. And see if you can get the max and mins right. Pause your video, come back and check it, and see how you did. Okay, so this problem definitely presented lots of different challenges. So first, to locate the extreme values, we had to take the derivative of f. Then, in order to solve for this derivative when it's equal to 0, we needed to use a double angle identity for sine, which says that if you have sine of a double angle, sine of 2 theta, or 2x in this case, that is equivalent to and can be replaced with 2 sine theta cosine theta. So I took my sine 2x and I replaced it with 2 sine x cosine x. But I still had this other 2 in front just from the problem, so I had to multiply those 2's together to get 4. So then I had 2 cosine x plus 4 sine x cosine x, and I'm trying to solve for when that equaled 0. So I factored out a cosine, and a 2 actually. So I had 2 cosine x on the outside, and then times 1 plus 2 sine x, and all of that equaled 0. I set each of my factors equal to 0. So cosine equals 0 at pi over 2 and 3 pi over 2. So those were 2 of my critical points. And then 1 plus 2 sine x will equal 0 when, if I subtract 1 and divide by 2, when sine x is equal to negative 1 divided by 2, or negative 1/2. So it's 7 pi over 6 and 11 pi over 6. And those were my other 2 critical points. I kind of put them in order along the unit circle. But then because this question also came with an interval, a closed interval, I have to also check those, because those will create a max or a min simply because the function is like cut off at those points. So I had to plug all of these points into this equation. 0, pi over 2, 7 pi over 6, 3 pi over 2, 11 pi over 6, and 2 pi. So I plugged all of those in. I'll just kind of walk through one as an example. So maybe I'll do pi over 2. So sine of pi over 2 is 1. And when you plug pi over 2 into cosine of 2x, maybe I'll show you down here. So it'd be cosine of 2 times pi over 2. The 2's actually end up canceling, and you end up having to evaluate cosine of pi instead, which is equal to negative 1. So that's how I got negative 1 right here. And then 2 minus -1, this became positive, was 2 plus 1 was 3. Now that actually ended up being my absolute max, was the 3. But this is interesting because I had 3 values of -1. And if you look at the picture here, so I kind of labeled where everything is. So this was the pi over 2 comma 3. You can clearly see that's the standout absolute max. And then these were the 2 of my, sorry, not there, right here. 2 of these were my -1 values. This was 3 pi over 2 comma -1, and then that was my endpoint, 2 pi comma -1, which relatively speaking, they were actually high points. Like if you ignore this whole part of the graph to the left here and we're just looking at this little neighborhood, these are technically like relative maximum values. Whereas over here, I also had another endpoint of -1, but at this part of the graph in this neighborhood, it was actually a relative minimum value because it was lower in respect to the neighboring y values or the local y values. So I wrote down here we had relative maximums that were equal to -1 when x was 3 pi over 2 and 2 pi, but then we also had a relative minimum that was equal to -1 when x was 0. So it kind of goes to show how you really have to check with the graph. And then I definitely had my absolute max of 3. That was my highest y value, and my absolute minimum of -1.5. That was my lowest y value. So those did prove to be my absolute max and mins because we were on a closed interval. So the highest is the highest and the lowest is really the lowest. So those are our absolutes right there. Okay, so that concludes this video, and I will see you guys in class for questions and clarification and all that good stuff. Thanks for watching. Bye.